Hi everyone, my name is Pratishta, and in this video, I'll walk you through my simplified solar system simulation project in Python. So, I first created a planet class that takes in two attributes, radius and year length. The radius defines how far the planet orbits from the Sun, and year length is the number of days it takes for one full revolution. The key method is position day, which returns the x, y coordinates of the planet after a given number of days. This uses basic trigonometry. So x is equal to radius into cos of angle and y is radius into sine of angle, where the angle is 2 pi into day by year length. So then the distance p1, p2 day function computes the Euclidean distance between two planets on a given day using the Pythagorean theorem. So, what is the distance between Earth and Mars on day 732? So, let's start running this code and see the output. So, as you can see, the Earth and Mars distance on day 732 is 6.52 units. So, after this, I simulated distances from Earth to Mercury, Venus, and Mars for 1000 days. I stored both the exact distances and the noisy version. The noise simulates sensor error using a normal distribution with mean 0 and a standard deviation S. So let's see the plot. Here, the plot on the left shows the true distances, and the one on the right shows noisy observations with S is equal to 2.0. Each line represents the time series for one planet, and dashed horizontal lines shows their average distances. So from this, we can see which planet is closest to Earth based on exact average distances. So the answer is Mercury. So what about when there is noise with standard deviation 2.0? Still, Mercury remains closest, as you can see. So I use transparency to make overlapping lines easier to interpret and added average markers for clarity. So to test the robustness, I varied the standard deviation from 0.5 to 10.5. Surprisingly, for all noise levels, Mercury consistently remained the closest planet to Earth based on average distance, indicating that its proximity is robust to noise. So, does increasing S change which planet appears closest? No, the ranking remains the same. Mercury still stays the closest. So, this behavior is expected because Mercury's orbit is the smallest. So, despite the noise, its signal dominates. So finally, I ran a 1000-year simulation, which is 365,000 days, and computed the average distance between all 8 planets. I created an 8 into 8 matrix and printed it using symmetric data frame. So to verify, we can see that in the output that the matrix is symmetric as expected. I then identified the planet closest to Earth on average over these 1000 years. So, which planet is closest to Earth on average? So, again, the answer is Mercury. So, this reinforces our earlier findings and shows that the model is consistent over different time scales. So, I use trigonometric modeling and Euclidean geometry to simulate orbital distances. And across all tests, Mercury remained the closest planet to Earth, both in ideal and noisy scenarios. Thank you so much for watching.